No? Yeah, so we are live on YouTube now. Welcome back to the session, day 3. So today I'll be, okay, yeah, so can you see my screen?
Yes, sir.
Yes, sir.
Okay. So I was not able to cover few topics yesterday, and we had to do the Tinkercad like really quick. I hope you guys went to Tinkercad and saw what it is, and hopefully design something. Uh, Today I'll cover few of the important topics, and then I'll go to a new software called Fusion 360. We'll look at how design is possible, how you can design in a 3D space. We'll look into that software. So after the session, I think I'll share you the link as to how to install the software and start using it. So I'll do one model in front of you. I mean, I'll demonstrate um, uh, the Fusion 360. Before that, I'll cover few of the topics that I was not able to cover, which are like more essential. Okay, so I'll mute all the participants when you have to speak. Only then you please unmute yourself and speak, and then mute again. Thank you. Okay, switching and gaining control of the motor. Yeah, so yesterday I was talking about how force is the cause for any motion, and we saw the effects of motion, center of gravity, force, torque. We calculated the speed of the robot. We looked at what are the different wheels that are available and what you could choose out of the options that are there. And we also saw few things about motor, their specification, um, and some concepts. So along the same lines, so when we are teaching motors, and we say you give voltage here, and the motor rotates. So now the kids would have experienced how a motor is rotating with a battery, right? And they would have learned how you can control the motor's rotation on and off, right? If you give battery and you have one switch also, if possible, then it starts rotating, and it also turns off. But how do you make it reverse? They would have figured out, okay, if I just reverse the polarity that is given to the motor, I'm giving positive to red color terminal of the motor, and negative to black color terminal of the motor. Motor rotates in one direction, say clockwise or anti-clockwise. It rotates in one direction. And you reverse the polarity, the motor is now rotating reverse. This I'm talking about the BO motor or the normal DC motor we spoke of. So those basic motors, you can simply reverse the polarities and the motor will start rotating in reverse. So how do you do that? See, the objective was, we saw the problem statement where we are building one robot which can be controlled through a robot. So that is what we teach them in the basics of mechanics, or the level 1 of robotics, for even starting from kids from third standard or fourth standard onwards. So if I have to do a remote control, how do I make the motor go in reverse? So there is an arrangement or a system called H bridge, wherein you are using four simple switches. So four on-off switches: switch A, switch B, switch C, and switch D, and you connect the motor like in this format. So now what you have to do is, by controlling the switches, yeah. So now what you have to do is, like, you are having a battery here, and positive here and negative here. So the current flow is off because all the switches are in off state now. See, all the switches are in off state. All the switches are in off state. The moment you want to connect this terminal, the voltage will come here like this. The voltage will come here like this. The moment you turn this off on, so the voltage will come here like this. So which means positive is coming to the plus of the motor, negative is coming to the negative of the motor. When you turn on A and C, when you turn on A and C, you are having motor in one direction. Okay. So this is A and D is on. Motor is in motor rotates in clockwise direction, clockwise. So the moment you, and remember, the switch C and B are still open. So the circuit essentially is like this. The current flow is like this. The current won't flow when a circuit is open. So there is an open here. So the current flows like this. So the motor rotates in one direction. Okay. What is the second scenario when I have to get the motor to uh, rotate in anti-clockwise or reverse direction? So what I do, the battery will still, the voltage is still here. So the plus is effectively at this point, negative is effectively at this point. I will turn on the C, I will turn on the B, but I will I will keep the switch A and switch D open. So how will that current flow? The current flow will happen like this. So positive is coming here, negative is coming here. So how will the motor rotate? It will rotate in the anti-clockwise direction. So by having C and B on, I am, and at the same time I am having A and D as off. So I'm reversing the polarities given to the motor, and the motor is rotating in reverse direction. See, this is called a H bridge. This is called a H bridge because you can see there is a H shape that is there. H. So hence the name H bridge. And this is the bridge where you have connected the motor. So this is the circuit connection for a H bridge. So by doing this, the problem with this setup is there are four switches, switch A, B, C, and D, which you have to control. The one problem that will happen is, suppose you turn this on and there is one instance where this is also on, but these two are off. Suppose such an instance happen wherein you are controlling four switches and an instance wherein switch A and B are on. So you can see there is a short circuit which doesn't flow through the motor, but it goes directly to the battery. So the battery or the wire, something will break. So there is a short circuit, which means the motor will stop rotating and your wires get burnt and battery goes boom. So this is where the problem is when you are having four physical switches. So what is the solution? What is the solution for this problem? We have these switches are called SPDT switches. They have single pole and a single throw. Single pole is one pole is getting attached to another pole, and there is one throw, one connection happening. So we have another switch called DPDT switch. Okay, dual pole double throw, which means they're essentially two switches side by side and they're fused together. One second. Yeah. So you see there are two switches, switch 1 and switch 2. They are fused together, right? When you press one side of the DPDT switch, okay, then you can activate this and you can activate this. You are making that connection and this connection is still off. So the center middle pins, these two pins, what happens is they are getting connected to the two upper pins. So that is the DPDT switch. Okay. So with this configuration, we are making a robot or a motor go in particular direction. Okay, now that we know we can control a motor, you can turn it on, off, and reverse. Let's see how we can use this function to build a robot. So you would have seen battle tankers. In the battle tankers, the way that battle tanker moves, right? The way the battle tanker moves, it has got left side track and the right side track. And the way the battle tanker moves, when there is more velocity or more power given to one side of the track, that side will go front, and this side will not turn, or less velocity is given. So the battle tanker is now able to turn based on more velocity and less velocity. So this type of driving the robot or making the robot move is called differential drive. Okay. So the other kind of drive that we see is a steering configuration, or a steer drive. It's all the automobiles, cars, trucks, everywhere you have a steering mechanism. Okay, but the steering mechanism has moving parts. It has one controller or a motor or an actuator, pneumatic actuator or a servo motor sitting in the middle of the mechanism axles, so that you are getting a turning radius. So any of your car, it will not have a lateral movement. The car can't move side by side. It will only turn about a pivot which is not within the car. So the car requires more space to turn. Okay, and you would have seen people struggling to take U-turn. If only the car could turn on itself, they don't have to use reverse gear also. But they have a steering mechanism. And why I'm telling all this is when you have a problem statement where the robot has to navigate through tight spaces and narrow spaces, say robo race or even playing soccer, if you have steering mechanism, the navigation of the robot becomes very difficult. You have to have more space to take turn and U-turn. The differential drive, you can turn about its own axis. We saw the Curiosity rover, it had 6 wheels, still it could turn about its own axis. Wherever it is standing, it can still turn. It had a combination of steer and differential drive. You can go watch any Curiosity rover video, you will find it has a combination of steering and differential drive, and it has got 6 wheels. So differential drive, I'm just taking example of a battle tank or a 2-wheel robot, and how you are able to make the robot go front, go reverse, take left turn, right turn, turn about its own axis. Slight turn also is possible by reducing one of the velocity or speed of one such motor. So you got the steering mechanism. There are many different ways of making a robot move or drive the robot. So we've got these special wheels that we spoke of, which is called the mecanum wheels. Okay, so here with the differential drive, what you are having is you need one such circuit. Say this, if you are considering DPDT switch as one circuit, this circuit, you can control one motor. See, one battery, one switch, one motor, done. You are done. Here you need 2 DPDTs like this. You need 2 DPDT switches. You need one more of this so that you can control another motor. You can use the same battery. So here I need 2 DPDT switches and 2 motors and 1 battery to have this configuration. Okay, steering mechanism, I will need just one on-off switch or one DPDT switch to make the robot go front and reverse, and another DPDT switch which will control the steer mechanism, turn right or left. Here with the mecanum wheels, it needs to have at least 4 wheels, because each of these wheels are not simply kept. It is the same configuration how you get a quad rotor or a drone setup. It has got same wheel, but it is flipped about 2 axes. So if you're considering this as a mirror plane, this wheel is flipped, and if you're considering this plane, this wheel is flipped. So there are 4 wheels, but in this kind of formation. This format is very important. When all of the wheels rotate forward, this robot will go front. When these, you just look at the arrow marks, it will tell which are the motors in which direction it has to rotate to get the lateral movements. So the robot, instead of going straight or taking slight turn, it is now going lateral, side by side, with the x-axis or y-axis. So now this robot can also turn around its axis about a pivot point. So it can turn around an axis situated in one of the center location of the wheel, contact point of the wheel, or it can find a midpoint. The pivot can be in the midpoint when it is rotating, or in between the 2 wheels, the midpoint can happen. But the thing is, here you are independently controlling each of the motor. If you have to have this, you can't have 4 DPDT switches controlling 4 motors. It is literally not possible for you to control 4 motors and make a robot go front lateral. So you will need a programmable board and a remote control to do this. Remote control in the sense it will send data front. Then you have to decode that data, say this is the user is telling front. So I will run motor 1, motor 2, motor 3, left motor, right motor, forward, all of that front, so that then I will do. So that processor has to be there and the controller has to be designed. But this has an advantage wherein there is extra set of movements that are possible. So when you are navigating, it is more precise. But the problem with mecanum wheels is, as you can see, it is not smooth. The contact surface is not continuous. So you would see the robot, will have some vibrations when it is moving front also, because of the undulations on the wheel. Okay, now we saw what are the different configuration. We know we need a DP/DT switch to control the motor and the robot. Now we'll look at very popular robotic competitions, and most of Arun was talking about the STEM pedagogy and how the robot ecosystem is, and what are the kids doing worldwide and globally. What are the kids when they say robot, what is it that they're doing? So I've picked up 3 such competitions or topics where you see a lot of robotics in the K-12 space happening. So first one is the sumo wrestling robot. You will have lots of competition even happening in India. In engineering college level, even students can participate. This is a sumo wrestling robot competition. So in any sumo wrestling competition, they will have an arena. One robot has to push another robot. Sometimes it is, they will put 5 or 10 robots in one arena and they say, okay, wrestle. Okay, the last robot standing would win. So in this kind of competition, it is better to have a very high torque motor. Because of the high torque requirement, what happens, the speed will naturally get reduced, and the center of gravity has to be kept very low. If you keep the center of gravity of the robot little higher, then it can tip over, it can fall. But if you put the center of gravity very low, the opponent robot has to lift your robot from the ground up. And for that reason, since everyone is doing the low center of gravity, most of the sumo wrestling robot that you see will have a slope in the front, that inclination in the front. This they do because, see, in the second image where one robot is getting pushed, that robot obviously is on top of the other robot. it is getting pushed and the whole weight is getting pushed like that. So because of this, the contact surface with the wheel and the ground is also reduced, because you are scooping the robot up. You are scraping the robot from the below. So sumo wrestling robot, most of the robots will have the slope in the front, and they will have very low center of gravity. And center of gravity in the sense the weight is concentrated in the lower part, the lower region of the robot. And there are multiple configurations, as in it could be remotely operated with RF remote or NRF remote, the modules that you get readily available, or even the wired wrestling robots are happening, where you can have DPDT switches and long wires running through, and you can still have that robots. And the slope is something that is inevitable. And usually in these competitions, the choice of motor, wheel, and how the slope is designed, how rugged the robot is, and what is the material that is used to build the robot comes into the picture. In some competition, weapons also you can use. So people have different ideas of how to destruct the opponent robot. So you will see how to protect your own robot and how to attack at the same time. So those are the things that is kept in mind. So the other
Sir, one
popular
question.
yes, ma'am, please, you can ask.
Sir, what is the role of center of mass as well as center of gravity, both in the robot's anatomy? You
Okay,
just explained center of gravity, but is there
correct.
any role of center of mass as well?
See, center of mass and center of gravity coincides at the same point inside Earth for a uniform distributed body, right? Center of mass and center of gravity. Center of mass is what? Where the mass is situated to be. Effectively, that is where the mass is situated. But there is a gravity that is happening, which means when the external forces are not there, center of gravity, because gravity is the only other force that is acting, center of gravity and center of mass will come into the same picture. But the moment you have other forces acting on the robot, like there is a pushing and pulling and all of that, along with gravity, how the weight is distributed also comes into the picture. And this is where center of gravity, center of mass, both we have to look into, because there is uneven distribution of mass. See, wheels are made of plastic and rubber, whereas the chassis could have been made by very heavy aluminum or steel or mild steel, which is heavier. And there are processor boards which are very lightweight, and there is a battery which is the heaviest part of the robot. So it depends where you keep the robot, the battery, and how you place the battery, and how you concentrate the weight to one point. So having center of gravity, center of mass, when no force is applied, which becomes one essential point on the robot, that has to be kept very low. The battery has to be kept very low. So that's what I meant when I said center of mass has to be very low. I hope I've answered your question. So I'll move to the next topic.
Yes, sir. Thank you. Thank you.
Yeah. So in the soccer robot, uh, there are competitions happening wherein multiple robots will play in one team, say 3 or 4 or 2 robots in one team. And so you will have one arena where obviously it is like the soccer rules, wherein you have to go score a goal. So there are different strategies where people use. They will have one mechanism which will hit the ball. It could be a hydraulic mechanism, it could be a pneumatic mechanism, it could be a spring loaded mechanism. You will load the spring and you leave it and it hits. Or you can simply have one motor with one stick rotating. So whenever the ball comes, it kicks. So you can control that motor as well. Or you could have just one blower fan, so that when the ball comes, you can turn on the blower fan and the ball goes off flying. So and they also have the guiding mechanism, so that they can dribble the ball to the goal post. So when you're building a soccer robot, you have to understand what is the friction that is required, and you have to go for that kind of a wheel. If they're looking for a wooden surface which is fairly smooth surface, then you don't need wheels that you would use for an all-terrain vehicle. You don't need wheels which lot of undulations and threads. You can go for a smoother thread, so that the contact surface with the smooth surface is more. If you use a wheel with lot of undulation and threads, then you'll slip. Even though you think the robot has more grip and thread, the contact surface essentially with the more grip and a harder surface is not effective. So the wheel is touching only at 1 or 2 points. So one small experiment that usually I ask kids to do it when they're choosing a wheel is um, paint over the wheel and ask them to stamp over a paper. So you will see the wheel track print. Then you can see how much contact area that is. So you have to know what is the contact area and how much friction it can get. So soccer robot friction is usually not a very critical aspect, but maneuverability is how well you can control your robot, how well the robot can turn on its own axis and move accordingly, and even there are autonomous um, soccer playing robot with image processing and sensor, wherein the ball would be of orange or a contrasting color, or the ball will be having lots of transmitters or IR transmitter or radiation transmitters, wherein the robot can detect or pinpoint where the ball is, and it will go towards that point. So robot will always be in a scanning mode. As soon as it picks up the radiation or intensity levels, it will turn towards that direction. It will go attack that ball. So you can even have autonomous robot and even manual soccer playing robots. So construction should be kept very simple, and maneuverability is something that you have to consider more. In terms of center of gravity, the choice of motors, keep it say 100, 150, 200 RPM. So it is fast enough and also packs with some torque, so that you can compete. When it comes to robo races, you have to find out what are the terrains, whether there are any steps, whether there are inclinations. If there are inclination, again, center of gravity, center of mass, you have to keep it low so that it is able to climb the inclination. If you keep the center of gravity above, then it will simply tip over. So what is the maximum angle of inclination that they will have in that arena? That is something that you have to find out. What are the different terrain that is there in the arena? Based on these factors, you have to decide how many wheels you will put and what is the different configuration that are available. In terms of RPM, if the track width or the terrain or the race width is small, the faster the robot, better advantage you will have. And obviously, students have to practice with the maneuverability. And having a speed control at the same time will give an added advantage in the robo race. There'll be points wherein they can ride very fast, and there will be points wherein they have to ride slow. So having a speed controller along with manual operation will have an added benefit, and we have seen how we have won competitions just by having a speed controller and having a very fast robot. And you will see interesting shape of wheels which could navigate the entire terrain, any sort of a terrain, but compromise of speed is something that will happen. So trial and error method is one of the best ways. Have at least 2-3 kinds of configuration built and try for those use cases for any particular competition that is. Okay, what? So
Yeah,
this
sir.
slide,
Yes, sir.
yeah,
Can you just move to the last slide, next previous slide, sir?
yes,
So
no,
it is robo racer. As these robo race are like they're not very heavy, as you can see in the
correct.
pictures. So I think, sir, when we are designing such type of robots, we have to be very precise with the center of mass.
Correct. So in terms of in any all-terrain robot, say there'll be different terrains. As the name suggests, there will be different terrains. As long as the terrain is hard enough, you have no problem with the weight of the robot overall. As long as you have wheels and the robot won't tip over. The second image you see, even if the robot tips over, it can still navigate because the contact or it is still symmetrical. Even if it falls over, it can still navigate. Right? But if the weight of the robot increases, it will sink into the ground. If they put some sand, loose sand, it will sink into the robot. If there is a puddle, you get stuck. Right? So we have seen in the all-terrain robot, even though it seems like the track or the battle tank, you saw the tracked wheels or this, those kind of wheels don't perform well. It is just the wheel, bigger wheels, wider wheels that perform well, because you can still gain more contact, and it's also four wheels that will drive, so it won't get stuck anywhere. So I've seen where track belt robots fail in all terrain. People will only think about the contact surface and not other things. Weight has to be kept very minimal, as minimal as possible. You can see that's why they have used PVC sort of a configuration, and they have not gone for metal. Instead, they have gone for acrylic. Even acrylic is pretty heavy. You can go for other plywoods that you can do. So when acrylic is a bit heavier than plywood, it is little more denser. So you have to look at the ways you can reduce the weight of the robot and have very minimal stuff. And wheels is what matters. And obviously, when it is a race, you have to control better. You have to take the shortest path. That comes with practice. Anything else? Any doubt here so far? Okay. So in terms of the key components, it's the remote, batteries, wheels, nuts and bolts, the choice of wires. These are the few important points. With the DP-DT switch, let me show you. Yeah, with the DP-DT switch, you will see there are two wires coming from each battery, and there are each battery and two wires for each motor, right? Suppose you have four wheels, four motors, and you have only two DP-DT switches. You can short the left side motors and the right side motors. Short the left side motors together and then short the right side motors together. So effectively, you are still controlling two. So you will still have 6 wires that is coming through the robot till the remote. So for that, what we use is an Ethernet jack, which has more than 6 wires. There are RJ45, RJ9, based on the number of wires that goes in. So we use this cable, the multi-thread cable, so that you can simply plug and it starts happening. So we built a breakout board which suggests, see the motor 1, motor 2, motor 3. So you can connect 3 motors and you can have 3 DP-DT switches and connect just one cable in between. So the link for this, whatever we did, is there in the YouTube. Once the slide is shared, you can go to the link and watch that video. Okay, coming back to our topic, we have to dive into the Fusion 360, and we have to design something. And just before we introduce kids to a 3D modeling software, we have to tell them why we are doing 3D modeling. Yesterday, one person asked me, why are we doing 3D modeling in robotics? So that I said I'll cover in the later stages. So there are few terms that few things that any designer, if you're building, has to do. Anybody will have an idea. Even I will have an idea. You will have an idea of how the world has to be, how a mobile phone has to be. Everyone would have had an idea as to what anything has to be. And if you are able to visualize that and communicate what your idea is, only then it will come to a reality. See, how you communicate your ideas, you can keep on describing, my wheel has to have this sort of a thread, it has to be in this shape, this size, and all of that. And that person would listen to all of this and design a wheel or manufacture a wheel, but he would not have used rubber itself. He would have used some metal or plastic, and he would have given it to you. So the best way that you can communicate an idea is through images or 3D model. So in the age of computers, if you are still drawing and doing it, fine. If you are able to create a 3D model and simulate and animate and show this is exactly how my idea has to be. So the communication is effective if you know a 3D modeling software. So even when you're building or constructing a house, you would have seen drawings. Most of the people don't understand what the drawing is, what the layout is. So now what they're doing is there are many realtors or real estate website they are trying to, bring in 3D modeling and a walkthrough into the space, a 3D space wherein you can navigate through and see. It's a 3D view of the space. They're creating 3D models. Why are they doing it? So you get a feel of that place. The same thing. You have to ideate and then you have to visualize and then communicate. This is only possible with doing 3D design. If you are not willing to learn, at least you have to, understand why this has been done. So when we are teaching the kids, so that is why we tell. So you have an idea, say I want a water bottle that can hold up 1 liter of water, and it has to have a certain shape. And the shape you are not able to define. You are not getting the right terminologies to tell. If you had one photo or a reference or a sample piece, the thing, I mean, you are able to communicate within the team, vendors, manufacturer and fabricators much better. So this is the context as to why we teach engineering, design, drawing, and 3D modeling software, so that they have any problem statement like build a robo race, they know, okay, for this chassis also, if they have to build the chassis where 4 motors will go, they should know what are the exact dimensions that they have to build, and what are the motors that they will connect, and how they will connect the motors and the wheels together, where they will place the battery, how do I house the circuit board on top of that. So for these reasons, engineering, design, drawing becomes a very essential tools. And the few terminologies that is very essential is objects, axis, origin, and projections. So any object that occupies space, anything that occupies space is an object which will have 3 things: length, breadth, and height, right? And these length, breadth, and height, you take a basketball for an example, it will have all the 3 things: length, breadth, and height, and also other dimensions to it like the weight, color, texture. But we are looking at the how we get the coordinates. So length, if you measure length of an object in one axis, you can't measure breadth of an object in an axis like this. It has to be 90 degrees. That is where you get length and breadth. They are 2 axes. They are 90 degrees to each other. So, okay, that is where you see this, you holding this finger like this. Okay, this is the Z-axis.
Perpendicular to each other.
Yes, each axis has to be perpendicular to each other. Okay, then you get x-axis, y-axis, and z-axis. Then you get coordinates. Which point on the x-axis, which point on the y-axis, which point on the z-axis. You get coordinates saying x, y, z. You would have taught these things to kids in CBSE, but I'm bringing in that Cartesian coordinates to how we use it in a 3D modeling software. So any object with height, length, and breadth, and how they are 90 degrees to each other. And in any 3D model, there are only 3 views that we look at. One is the front view, one is the side view, and then there is a top view. So how do you get side view? You place one torch and there is a shadow that forms, that is the side view. You get front view, you get top view. These are the 3 views. How you place them on a drawing sheet? This is how you place them on a drawing sheet. When you give it to a designer, this is what you give: front view, side view, and top view. So of a bottle, these are the projections. Why we need only 3 images are sufficient? You might ask. Because only 3 images are sufficient, because all of these projection will also have edges and invisible edges. So for this bottle, there is image from the bottom. If you look at this bottle, okay, for this bottle, if you look at from the top, there is another indentation that is happening. Even this information has to happen, right? But for a drawing, top view, front view, side view, when you look at this from this angle, so the top view of the bottle, you don't simply write what you can see. You also have superimpose what is on the other side. So it is 2 images, the front image and the back image superimposed. So you have all the lines that are there in the front and the back superimposed. So that is the top view. The same with the front view. You don't just write what is there in the front that you can see. What is there in the back, that also is there, and that is superimposed and kept. So that is front view, side view, and top view. So it's a view, but it is actually a projection. That is why I've used the torchlight and the paper. So these concept we will tell them, and then see. If I had time, I will elaborate on these things, but I want to move to other aspect, why we do 3D modeling. So if you look at all the models that we have built so far, all of our models, see even this model, say walking robot, the biped robot with the servo motors, or a simple gear and cam mechanism of this cat and mouse, or the remote control robot that we have built, we have used one technique, which is laser cutting technique. So we will get into that aspect. Wait. So laser cutting. So why we use laser cutting? Laser cutting is high accurate, and 3D printing will take a lot of time, but laser cutting, it is much faster. It is almost like a printer, or a laser jet printer. How fast you get a printout, almost at the same speed you will get the laser cutting done or laser etching done. So so just do the for this we will take about 10 minutes to cut the entire base robot. For this we took about 30 minutes to laser cut it, right? So we use these materials, say MDF, cardboard, plywood, acrylic, even aluminum, stainless steel, mild steel, as long as their thickness is not beyond something that the laser can cut through. And laser cutting is only two-dimensional. I mean, when I say two-dimensional, it will only cut like this. It won't cut in an angle. So it is only two axes it can go through. So anything, any drawing flat image that you give, it will simply cut and give. Then you have to pop out from that thing and you can start using it. So all our models, see the chassis doesn't have any other faces. It is just one face because it was laser cut. And now then we had other parts that was again 2D laser cut. Then we are using it this way and we are forming joints. So what are those joints? We use dovetail joints, finger joints with fasteners, and snap joints. These are the joints that we have used. And these two robots that you see is a robotic arm, and this is a mobile robot that we have built. We built these two models using only one software, which is Fusion 360, and we used only one manufacturing technique. Other than one or two 3D model parts, 3D printed parts, all the things are 3D modeled and laser cut. We used cardboard, we used MDF, we used plywood to do the laser cutting. Okay, so that's about introduction to laser cutting and why we use 3D modeling and laser cutting side by side, so that we can start building such chassis. So if you have an idea, you can dive into 3D modeling software, generate a file that you can give to a laser cutting personnel, and they will cut the material and give it to you. Then you can simply attach the motors and wheels, and then you're good to go. So shall we start with the Fusion 360? Today I will start the Fusion 360. I will demonstrate what is the interface, workspace, and I will go through it. After the class, I will send you this thing, the link to install the Fusion 360. It is free for an educator and a startup. It is free, and it comes with it's for a short period. It is for 1 year, and then you have to pay for the services. So since it is free and it gives you a head start, then you can even consider buying other proprietary software which costs money. So I'll stop share the screen and I will again start back sharing the screen once I launch the Fusion 360.
So can you tell what are the hardware specification for Fusion 360?
Hardware specification for Fusion 360. Yes. So for Fusion 360, you need a good RAM. So any RAM more than 4 GB is good. In terms of OS, I'm using Mac and Windows 7. It is working fine for me. And in terms of the processor, uh, um, I i5, i3 also has worked. Um, uh, The thing with Fusion 360 is it is cloud based. Whatever you do, wherever you share, the project you do, you can access it in different computers. It is cloud. I mean, it keeps saving in the cloud. So what happens is you need to have a very good internet connection when you're doing Fusion 360. So I will share few things. I'll just come back to it. I don't have the exact minimum specification on top of my head. I didn't consider that aspect. Sorry. So the RAM is something that has to be more, and that is 4 GB that I'm pretty sure of. In terms of processor, i3, I think it is minimum to have i3. Dual core and all, probably it won't work fine. Okay, so once you launch Fusion 360 and 1 second. Okay, once you launch Fusion 360, this is what you will get. And you can, so sorry, this is what you will get. This is a home button. I've created a lot of models and you can see a lot of projects as well. So what you can do is you can start a new project. So I'll just say new project and say demonstration. Okay, demo. Fine. So I'll just hit OK. So now I have a project called demo. I'll enter this folder. This is where I can save this file. Okay, then I will go. First thing I'll do is save it. Even though I don't have anything, I'm saving it as demo. ATAL. Okay, I'm saving it. So this thing is saved and it is kept there. You see the blue thing. Whenever you see a blue thing, which means it is interacting with the internet and it is saving in the cloud. So I can go open any of the other computers where the Fusion is installed. I just have to do the sign in. So this is my account. I can sign out here and then I can access from there. And also you can collaborate. Suppose you have a team, say 4 students are there and you are there. So you create this project. You save it once, then you go to people, you have their email address and invite. So they will get an email. When they click, they will come here. So you will see a new person getting added here. And whoever created this project is called a moderator. Only a moderator can give access to people in the project. So this is a project that I have created. So this is the 3D space. Again, you can with the same like Tinkercad, you can look at. So there is something called as timeline in Fusion. Okay, every movement that you do, are you able to see the screen? Okay.
Yes, sir.
Yeah.
Yes.
So in the Fusion 360, I can just close this. Okay. So in the Fusion 360, there is something called as timeline, where you can play, you can do all of this. This is the timeline that keeps building up. So right now it is empty. You can turn on the origin. You know what is origin, right? That's the starting point. So once you have an origin, now you can start having models here. Unlike Tinkercad, this doesn't have an object that you can simply drag and drop, but you have to build it up. So there is create and then you modify. So the first thing that you do in the Fusion is you have to create it. Okay. When I press create, so I get something like sketch. Okay, one more thing. In the Fusion 360, there are different modes. Whether I'm doing design or generative design or I'm rendering. So I've designed something in Tinkercad or other software. I'm just putting it here and I'll take nice photos of it. So that is render. And you can do animation. So there are assembly information like how to assemble 2 components. So those animation you do. Then there are simulations like how the stress is happening. You can add materials to it. Say this is made of aluminum and what are the heat treatment. If you have done aluminum, it shows what are the different materials it is. And then you can tell what is the fixed load, what is the dynamic load, what is the impact that it has to sustain. Then you can simulate it. It is a little more advanced. You don't teach these things to kids. Animation is something that we teach For little, we just explain them the interface and they will take it from there. Manufacture workspace, this is something that we again don't look at. Drawing, yes, because this is where we generate the drawing and share it with the laser cutting manufacturers. So we share the drawing and he will manufacture and give it to you. So today I will do one thing. I will create one pen stand. I will create one pen stand. I will take you through what are the tools that are there and how you can do it. So the first, okay, I'll just take what are the questions. Can you please give us link of Fusion 360? I will share it as soon as this thing session is over. And how to laser cutting. So laser cutting, you have to generate a file that you can send it to the laser cutting people. This could be a simple vector graphic or an SVG file, like how you have JPEG and PNG for images. You have for the lines and vectors, you have SVG. So SVG is one thing, DXF is another, and then you can even send a PDF, printed document file, but the PDF should not have a lot of gradients and images and all of that. It just needs to have the lines that they will use for cutting. So they will only extract the lines from the PDF and they will cut. If you have some, yeah.
It is the same thing like how we work on Tinkercad and we can do 3D printing.
It is
once we save the file of
yeah, so in Tinkercad they also have an interface. It is integrated with the printer software as well. So it the slicing and all it will do and give the Tinkercad, or you can just generate an OBJ or object file or stereolithography or STL file, right? You can generate STL file or object file, import into a 3D modeling software, the software that comes with the 3D printer. You can import it there, and then you can do the slicing and add the hanging structure, supporting structure, and then you can do all of that. What is the infill? You can set all of those things. Here also you can export anything like that. See, there is an export option where you can export the designs to different formats, and you can even import different files into the 3D modeling. Suppose I don't want to design something, I can just go to websites like GrabCAD, where you get a ready shape, somebody build it, you just import it here. So you can even do that, and once you import, you can even modify those designs. So 3D, I mean, Fusion 360 is quite advanced that way. You can do a lot of things. Your YouTube is not starting. Please, okay, this was long back. Will it cover all direction? These, okay, directions of the robot is covered. How to laser cut? Yeah, so you can generate these files to do that. Do we need to install Fusion 360? Yes, you need to install Fusion 360. So now we'll start modeling something. So we have a 3D space. Suppose you are not seeing the origin. Origin is kept here. So our origin, I'll turn on the origin. See, learning Fusion 360 is at least 10 hours.
Sorry to intervene. Can you please be a little louder?
Okay. Okay. Can you hear me now? I think there's some lag issues, I feel.
It's okay. It's all right.
Is Blender software enough to do all that is done in Fusion 360? Yes. All that is done in Fusion 360, I wouldn't say in terms of getting the laser cutting done, you can do it in Blender. But you want simulations to happen, you can't use Blender for such simulations. There are other engines in Blender which is of much better use. Okay, so in Blender you can animate, you can have physics, and you can have two things colliding. You can have things getting splattered. There are particles that you can animate and all sort of thing. In terms of just getting STL file or an SVG file, you can do it with Blender. Even Blender is free and you still have to install it. Okay. So now what I want to do is I want to create something. So I spoke of projections and the top view, right? So the Fusion, everything is about projection and top view. So there are new things that are added, like create form and other things. We'll stick with the basics first. So we'll click the create sketch. So now I'm in the sketch mode. design mode where I'm sketching it. So I have to choose which plane I will sketch. So I want to sketch on the bottom plane, XY plane. So this went to the top view now. So here is what I can sketch. Now I have the options that I saw is different. I can draw lines. I can have points, right? If so, what I do is I'll just draw one rectangle or something. Suppose I want to, okay. So if I draw a rectangle, I'll click for the starting point, and again I have to click for the end point. But when you click for the second point, you are committing to that dimensions. Before you click, you can type in what is the length or breadth of the square that you want. So I want 20 mm, which is 2 centimeter. I press tab, so it goes there, and I want 15 mm. So I got this thing. Once I'm done with this, I will press enter. Now I have a shape which is defined by dimension. So I've got this one shape which is 20 by 15. Now I will I'm still in the same sketch. I can keep drawing. I can add more shapes. I can add more shapes. There are multiple options like polygon, arc, circumscribed, inscribed, edge polygon. But the different ways of creating such shapes, you can even create slot. You can see you have this slot where the nut and bolt can go, and it becomes adjustable also. So you have a lot of these things. You can even add text and exclude text. So this is a 2D drawing, right? Now, once I'm done with the sketch, I can say finished sketch. So I still have the sketches that are visible. If they are not visible, see, before we just had one thing, origin. There was nothing. Because we created sketch, I see one sketch. So now we have two things. One, there is origin, and then there is sketch. I created one sketch. I can turn the sketch on or off. When the sketch is on, when you press extrude, okay, you press extrude, or the shortcut key is E. Okay, if you don't want to use a shortcut key, or if you're having trouble recalling what that shortcut key was, you go to create and extrude. The extrude function will create an object or a body. So I'm clicking extrude. I will select those lines which are closed lines. If you have just one line that is written, you can't extrude a line. It has to be a polygon. It has to be a polygon. It has to be a set of line where starting and end points are meeting. So once that is there, Fusion always have this pop-up window that is coming up. Okay, it says you select a profile. So I select this profile. Okay, now I can simply drag it. Now I have an object. I've simply dragged it, but I've not pressed enter yet. Once I press the enter, I commit. Enter is also me going here and pressing OK, right? I can adjust what is the height that I want for this rectangle. This could be 20 or 30. So I just wrote 30. So this I'm only adjusting one side, right? So this is the distance that I am doing. There are other things like one side or two side or symmetrical. If I do two sides, it will consider that sketch to be in the symmetrical plane, and it will happen on both the sides. If I do two sides, then I can have independent control. What should be this thing? Okay. And once I press OK, before that OK, you will have another thing called whether it is a new body, or you're joining it to another body, or you're cutting through another body, or intersecting to another body. But I want this as a new body, not component. I'll come to the component little later. So I want this to be a new body. When I press OK, from that sketch, okay, from this sketch, I can always go back and select more points. So I just created one body with one sketch. So I have one sketch and one body, right? So you see there was just origin, and then we created a sketch. Then we also have body. Okay, sketch you can toggle the visibility. Then again, you have body, you can still toggle the visibility. You have one body. You just double click, you can rename cuboid, or what is this shape called? Okay, I don't really know, but I'm guessing it is a cuboid. Okay, though it is not a cube, but I think it is called a cuboid. So we have created one object which they call it as body, and you know the dimensions also. When you click on any of these edges, you will see on the right bottom corner, it says you have selected one edge, and that length of that edge is 45 mm. Okay, and when you click on this profile or the face, it says you have clicked on one's face, and the area is this much. Okay, now what are the things that you can do with this? I can move this body around. To move this body, what I can do is I press the shortcut key M to move. Then I have to select which is that body that I will move. Then these coordinates appear. I can move it around different axes. When I move around, by how much distance it has to move, you can even do it manually, or you can type it here. So it moves the precise number of steps. So I can move this around. I can even rotate in different angles. Okay, I don't want to apply these changes. Now we have created a body. Now we are applying transform to the body. We are making the body rotate and do all of that, right? As you can see, there are two actions that we did. We turned on the origin, and then we created a sketch, and we created a body out of that. We used one function called extrude, right? So there is this thing in the timeline. It shows you created a sketch and then you did extrude. I can go back to that extrude and say edit feature. In the edit feature, I can alter all of this. I can choose not to select this profile at all, but have this profile. Now I press OK. Now the body is different. It is still saying cuboid because the extrusion or the way it created it happened with this sketch. So the link of that body is through the sketch, right? If I have to go to the sketch, I can right click and edit the sketch, or go back in the timeline. Like how I edited the extrude, I'm going back in the timeline. I'm doing edit sketch. When I'm going and doing an edit sketch, what I can do is I can modify the shape of this. Okay, I'm modifying the shape of this. When I say finish, you still have this, but I can again edit the feature. When I'm selecting the profile, I'll select only one part. See, you got this thing. So now, so you know how we are able to generate the body, move the body from a sketch. You are creating more bodies. So when I want to do another sketch, what I can do, I can simply go to create sketch or go create a new sketch. I'll just select which plane I want to do the sketch. Then I will start, the option appears wherein I want to create the chassis of the robot. So what I did, I want it to be a rectangle. You will have a problem statement. Your robot has to fit within 30 by 30 of space. This has to be the maximum dimensions of the robot. So you know what are the dimensions that you have to work with. So I kind of have an idea. Okay, I want the robot to be 30 centimeter. Okay, that is 300 mm, and 25 centimeter, so that is 250 mm. So I have this. To zoom out, I do left scroll. When I have to pan, again I'll click the mouse middle button and then hover so that you get to pan. So now I have this thing. Now I need a motor that will go there. So I don't know how the, one second, there's few questions. Was attendance link shared? My network is slow today. Attendance link is not shared. Okay, one second.
Yeah, we'll be sharing it. It's not a time, right? We'll share
Okay.
the attendance link.
Yeah, sure. Would you share the video recording of the tools? It is all, yeah, it is already there in YouTube. It is live streaming and it will be recorded and kept. And we have more videos where you can, go and learn more of Fusion and how to use this Fusion. See, Fusion is at least 10 hours, 15 hours of learning time. And then at least you have to work for the next 1 month, spending at least 1 hour every day to figure out all the options in Fusion, if not all, most of the options in Fusion. So until then, you will not simply get it. So I'm just telling you very basics of Fusion. So you don't, there is no hesitation to launch Fusion and try out few things. Once you start trying out few things, you can start doing more things in it. So this is just, I'm just breaking the ice so that you get more comfortable with things. So now I know this is the chassis, but I want to have some construction lines. I'll tell you why I would need some construction lines. I'm taking the line from the create, and I'm creating the lines. When I hover over any of these edges, you see the cursor is changing. I'm getting some triangle which says it is a midpoint. I can draw a line from that midpoint to this midpoint, but I would rather have it here like this. So I have a line. When I press extrude, I have to now select two profiles, two closed loops, which is the first rectangle we saw. Now that has been split into two because we had a line starting from one edge to another. If I don't want that, what I can do is I can go to the select. I can select that particular line and press X. So I'm changing into a construction line. Okay. I want to draw another construction line. So this is the symmetry line of our robot. So I have this thing. So and I will just press X. Okay. So if you go back and look at what is it that we are doing actually. Why is this not coming? Yeah. So now I'm trying to build this chassis that you see. This is the chassis that I'm trying to build now. I will not go with the exact dimensions, but I will take some arbitrary numbers to do this. If I have to take an exact dimension, I have to have one vernier or a scale with me, and I have to take each measurement, and it will take a lot of time. So now that I know there is a motor that will sit here. There is a motor that it will sit here, and I know there is a wheel that will come approximately here. Approximately the wheel dimensions are about this much. So I know these are the things that are there. Now what I can do, instead of again drawing the motor here, this is the top view of the chassis that I'm trying to do. So instead of doing that, what I'm doing is I'm going to the mirror function. You see, this is the mirror function. Mirror function, you have to select the objects that you want to mirror. In the mirror function, you have to select the object that you want to mirror. It could be a line, or it could be the entire closed loop. So if you double click that line, then it will look for the entire loop that is connected to. And I want to mirror this wheel onto the other side, right side also. So what is the mirror line? This is the mirror line. This is the mirror line. So I get the sketch or the rectangle drawn here also. Okay, I press OK, but I wanted to do this motor as well. So what I do, again, I click mirror. I will double click this for the motor. Then I will go to the mirror line and press this mirror line selection. Then again press the symmetry plane and I click OK. So now I have a basic layout. This is where my motor will go. This is where my other motor will go. This is where the wheel would come. And I want to see if this entire dimensions fit within the problem statement that was asked for. So there is an option called measure inside the inspect. So you click this edge and this edge, it will show what is the distance between these two things. You can't change or alter these things, but you can see how much that is, right? It is just inspection, you can't change it. But if I click the dimensions here, say 250, if I make it, I have understood that this is more, so I'm making it 200. Then you see how when my motor got shrunk. This is happening because I didn't give a dimension for the width of the motor. I have to define. So I'm pressing Ctrl Z to go back and undo. Then I will do it and I will see how this entire thing operates. So I want to do Ctrl Z. So I have this layout. I want to change the width of the robot, but the entire drawing is not constrained. There is no relationship between this loop and this loop. So when I change this dimension, this arbitrarily it is changing, the mirror plane is shifting and all of that is happening. But if I define this dimension, say to define the dimension, I will click D and click the link that I want to define. So this will be the width of the motor, which is say 5 centimeter. Okay, now the width of the motor is defined. Now there is another thing that I want to define. So, okay, again you can click D or you can select the sketch dimension, D. So when you click two of these edges, it will say what is the distance between the motor and the wheel. This is probably say 0.5 mm or I mean half centimeter. So I'm clicking 5 here. So this is the distance between, yeah, I have to click enter. See, the wheel and the thing became here, but the problem happened because the width of the wheel was not defined, the width got increased. So let's define the width of the wheel also. So what is the width of the wheel? Say 35. 3.5 centimeter width of the wheel. So this looks good enough to me. Okay, then I will again go to select. Okay, now that I have defined the width of the motor, width of the wheel, the distance between the wheel and the motor, if I change the width of the chassis, so let's say I will put it 200 again. Let's see what is the thing that happens. See, still the width of the wheel is still the same, width of the motor is still the same, but the entire chassis width has changed to 200. I feel this is little short, so what I feel, I will change it to 400. I want the robot to be big, so I made it 400. See, the motor is still sticking to the edges, nothing changed. But the moment I change the length of the motor, which I've defined it to be 30 centimeter. Now I'll make the length of the robot to be say 500 or 50 centimeter. Sometimes what happens, the motor length also changes and the wheel's length also changes. It will change this way. I will show. Since you have not defined it, okay. Since I have not defined it, the width could have changed. So I will define what is the dia of the wheel. So the dia of the wheel is about 100 or 10 centimeter. See, what happened is now it is not centered with the motor. So which means this rectangle doesn't have any constraints. It doesn't understand the position of itself in terms of motor. So you should have created one line here like this within the motor, which is the shaft line. Okay, then make it a construction line. And also you have to define what is the shaft with respect to the motor's length. Okay, you define this thing. So okay, so now I know the shaft will always be here with respect to this edge of the motor. Okay, then if I use this and then align the midpoint of this, then if I change, the wheel would not have been changing the dimension. Okay, now I want to create mounting for the motor. I want to create the mount for the motor, and most of the motor clamp will have holes like this, which I'm drawing with a circle, right? So I'm just drawing a circle, but the circle will have what is the diameter of the nut and bolt you will use. That is the diameter hole that you have to create. So that the hole is about 3 mm for any this thing. So I'm creating 3 mm thing, but I have not defined where that hole is with respect to the chassis. So I will again go to the line. I will define from the center of the circle to edge of the robot, what was the dimension? I will mention that dimension and I will enter it there. So the hole is positioned where it has to be positioned in the chassis. With respect to from the top edge, it is defined. With respect to the side edge, it is not defined. So I'll do this as well and make those lines as construction lines. I'll make those lines as construction lines. So the hole will stay there in that particular area. And for this, you have to know what are the clamps, mounting holes of that clamp. The clamp is that L clamp that you get wherein you put the motor and you put nuts and bolts. So how you put the nut and bolt, where you put the nut and bolt, instead of drilling it using a drill bit and a tool, I'm doing what? I'm getting this sheet laser cut in this shape with the holes also. So I can simply connect the motor and the L clamp. So there are other, now I want the same holes to be repeated here. So I'll use the mirror function. I'll just click on that loop and then select what is that mirror line. Then I'm selecting this mirror line. So you would see the hole is already there. Okay, I have to press OK. See, that hole is come here. That hole is come here. The 3 mm hole is repeated here. Now, if I'm doing a 4-wheeled robot, I would want all of these things to repeat here itself, the 4 wheels. And I don't want the chassis to be 500. I will change it back to 300. Okay, this looks all right to me. Then I will use the mirror function. The objects that I want to choose is the motor shaft, wheel, and the hole, the mounting hole. If it is 1 hole or 2 holes, whatever that is, you just select that as well. You just keep a track of how many objects you selected. Circle is 1 object, whereas square is 4 objects. A pentagon is 5 objects. Okay, so right now it is how many objects? 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. So I've selected 10. When I select this as well, which means I have to get at least 20. So I have to keep track of how many of these I've selected. So I got 19, which means the mirror function did not work. I have not selected the mirror function. So when I mirrored this thing, the mirror did not happen. So the mirror happened for the center point instead of that loop. So I'm selecting that object. Okay. Now you have this thing. You will see how this is what it shows. See, this is mirrored. The center symmetry plane, and there are 2 things that are mirrored. That icon appears when you mirror something.
So, to each side, it is considering as 1 object?
Each line it is considering as 1 object. So this you have to keep track when there is a complex shape and you are selecting a lot of things. When you mirror, then you will realize 1 shape I did not select. You have to again do it. But if you have sent it to laser cutting, it would leave that 1 mounting hole and it will give the other things. For that mounting hole, you have to again go back and run for a workshop and have 1 drilling machine to drill it. So keeping track of things, what am I doing, and reviewing it over and over again and using the inspect function every time will ensure that you have a design in the first iteration. You don't have to do multiple times. So that is why we all make mistakes. So that I'm just telling what are the tabs that you have to keep so that you don't make such mistakes. So one is having the construction lines where you define all the shapes with respect to the origin or other shapes. So I'm taking this entire rectangle as the main shape and I'm defining the position of this wheel with respect to the position of this main rectangle. The best practice is to have this origin. So you start your design from the origin and define every other object's position using construction line with respect to the origin. That is the best practice that you can do. It is little tedious, but once you do it, then there is no error that will happen from your side. Okay, now I want to repeat the motors and things. You see that this shaft line was not mirrored when I mirrored the motor. So I will again click the mirror. I will select the shaft line, and I will select the mirror line as well. So the line comes. So then I press OK. Then I want the entire thing to repeat here on this thing. So we are building a four-wheeled robot. So I'm clicking this thing. I'm selecting, double clicking for the entire loop to be selected. Then I'm also clicking this. Then I'm ensuring that I'm clicking the hole and the outer line and not the origin. So okay. Origin in the sense center point of that circle. Sorry, it's not origin. So I'm again circle. So 11th object is selected, 12th, 13, 14, 15, 16, 17, 18, 19, 20. So I've selected 20 objects. Now I'll go to mirror line. I will select this. Now see, I've got the same thing repeated here. So this could be our chassis, right? So what is the next thing that I want to do? I want to extrude this. So I can finish the sketch. I can definitely finish the sketch. Once I finish the sketch, we have two sketches actually, right? You have two sketches. You can turn on the sketch. There is already an object which we don't like, which we don't want anymore. You can delete it altogether. Deleting means it will not even have an influence or a tab that is created in the timeline. I'll go back. I'll do Control Z. Yeah. So I'll just go back, and when I remove it, removing is a little different thing. Okay. See, it is still there. That object is still there, but it is not showing up here. But in the timeline, it is there. I can go delete this feature, then the object appears. See, object appeared. So the key difference between removing and deleting is something. Deleting will ensure that the whole thing is out from the fusion. If you're removing, you have a trace of that object in the timeline, but you don't want it there. You don't want to see it in the bodies also, because in the bodies, when you're exporting it in a 3D other 3D spaces, or you want to get a 3D printed, or you want to laser cut it, that will come there. So I don't want it at all. So I'm just deleting it off. I don't want this at all, because I used it for something and I don't have any use for this. So I will delete it. Delete it is like completely taking it out of the timeline. So this deleted, I just deleted it. Even the sketch I don't want, I can delete it. Sketch I can delete, I can't remove the sketch, but I can hide and do this. Now I'm just hiding because I don't want it. I might want to go back, I don't know. So I'm just making it invisible. This is the sketch I want. Now I want to extrude. So what is the extrude feature that we have? We have a shortcut called E. When I'm extruding, whenever I click on the profile, it selects. When I extrude, see, this is where the motor will come, but my chassis will still have material, right? Motor will sit on that thing. Okay. And wheel is something that I will not extrude now. Wheel is a circular object. I don't want a rectangle. I just did it to visualize. So now I'm just seeing if I have given, if I've selected holes or not. If I select, even the holes are getting filled. I don't want it. So some profile, if I select, it got selected. Now it is all one thing. When I extrude, that also is coming, but I don't want that to happen. So I'll do one thing. I'll just unclick that. I can select, and again, if you click, you can unclick. So I'm selecting all the profile where the extrusion has to happen. So I want this. Okay, now I got this, but you are laser cutting it, right? Even though you're laser cutting it, it only takes the top profile of the thing. You just need a line. You don't, the thickness is not something that we have to consider now, but still, for the sake of it, I will still consider my material and what thickness it is. The material that you get in the market is something that you should know whether it can be laser cut or not. If you are able to laser cut, what is the thickness that you are giving? Okay, so I'm laser cutting it. From experience, I can tell it can easily laser cut anything which is very thin, say 1 mm and above. If it is less than 1 mm, you will see the material will get bent and warped and all sorts of things. Like it is a different case, you can cut even thinner things as well, but it might catch fire if it is very thin. The burn marks will take out more material. As the thickness increases, the burn marks from the laser is also something that we have to consider. Here, I think it is
So the video is paused.
Yes, we can't hear also.
sorry, there is some problem with the power. It got reset. I hope you can. Okay, we are again live on YouTube. It is happening. So I'll share the screen now. Sorry for that interruption. Yeah. So I was telling, now we have a sheet which you could have gotten cut from anybody, from hacksaw blade, or that blades or automated blades. You could have gotten it from somewhere, but the point is you got the holes precisely in those positions where when you use those holes and mount the motor, you know for a fact that there is no deviation. If you're mounting the whole motor like this, if you mount the motor like this, the robot will always tend to go in on particular angle. So alignment of the motor is something that is very important. And when you're laser cutting it, the accuracy is something that is taken care of. When you mount the motor, it will always be in a particular angle. So that is why we are doing laser cutting. So once we laser cut it, how much more time I have, I'll just try to wrap it, and I'll try to continue with a little bit more in the coming sessions. So so we have a chassis, and we have created this plate. Since you are laser cutting, you can give a lot of things. So that once you have done the create part, wherein you have created shape, there are a lot of things that you can go and look at also. Now that any shape is formed, or an object is formed, you can modify this form. So I'm adding fillet. So I'm adding a fillet like this. So it is a rounded edge. So when people touch and handle these material, they don't get cut from the sharp edges. So it's a practice at Just Robotics that we always use this fillet so that it is friendly to use. For kids, it is friendly. They're not handling with any sharp objects. So by the way to use fillet is just go to modify and press F, or go and press that option fillet. Then you select all the edges you want. I want this edge. I want this edge. There's another edge that I selected. This edge. Then what is the fillet radius is something that I've decided. Okay, that is something 5 mm or 1 centimeter or something. Then I press OK. So we got the fillet also done. So this is how it looks. But if we apply a fillet to any other edge other than this, say, I'm adding a fillet here. So I can have this object. Okay, I've added fillet around. See, it's almost like a tab or something. There is a fillet, a smooth surface running around the entire loop. Now, if I take a drawing of this, I'll just take this drawing from this thing and then we will end the session. We'll again come back and Brijesh will talk about H-bridge and the electronics in the robot. So I'll go to we were in the design phase. Now I want to create a drawing. So from the drawing, and it again has a pop-up window, whether full assembly means all the parts, or I can say select. So I can now select which are the components, only those components I can have drawing. Suppose I have a motor, it makes no sense for me to have a drawing of motor and send it to the laser cutting personnel, right? What is the sheet size? So what is the A4, A2, A3, and what is the sheet where this needs to get cut? That is something that you can enter. And that sheet size should be fitting within the A0, A1, A2, A3, A4. So I know I will take A0, which is the biggest sheet, and all the units are in mm, and I'll press OK. So it generates a drawing. I'll just wait for the drawing to come. It will take some time. All this while I'm using this, and everything is getting saved on the cloud. Even if there is a power cut, I know for a fact my design is somewhere there sitting and it will come to me. So once the drawing is ready, it is in a different view. I wanted the top view of this, so I'll change the orientation to top view. Now I'm able to see this, but there's some scaling also happening. So I'll see what is the scaling that has to happen. So I will go for 1:1, because when I do laser cutting, the 3 mm hole has to be 3 mm hole. It shouldn't be 5 mm or 9 mm. So that is the scaling. Then I go to what is the style that I want. I want invisible edges also to be visible. So I'll click that and I will do this. I will place that and I'll press OK. Okay, this is the file that will go to the laser cutting. It has just one line that it will laser cut. So when you press, when you send this, you don't include all of this. It is okay. Or you can have your name and all. You can add text. You have any note that you have to send it to, saying you cut this in 5 mm black color acrylic. You can type there, and okay. And then if you have a doubt that this person will scale it, you can even add a dimension. You can add a dimension and select that thing, and you can write the dimension. Or you can even show what is the center line and all of that. But when you're laser cutting, try to keep it very minimal. Just have this one thing, and also probably avoid text also if possible. Text also, you can, if possible, you can select that and you can hit delete. It will go now, or you can just move it. You can just move it out of the screen. And once you have done with this, what you can do is you can just go to output and output the PDF file, or output sheet as DXF. Out PDF and DXF is something that they will know. Any laser cutting manufacturers, they will know. I can extract that drawing and I can feed it to the laser, and it will cut that file and give. So we usually do it with the PDF and sometimes DXF. The problem with DXF is scaling problem. You can transform it, you can extend it and all of that. With PDF, you can't shrink that image. So I'll export it as PDF. It asks if all the sheets are, you can even have multiple sheets. You can have multiple sheets and you can keep adding drawings at each stage, and you can have different projection views also of that thing. So that is something. So when I'm outputting this thing, I don't want all the sheets, just the current sheet, and open the PDF once it is done. Whether you want to see the line weights, I will say okay. So where you want to share it, I say desktop. It is sharing. It is saving it in the desktop. And now it opened also, right? You can zoom and see how the drawing has come. So that is how you can create. Yeah, so I think I'm ending my session. Thank you so much. You have any questions you can ask. I think I took 10 minutes more, 15 minutes more than what
Hello,
I was
Vaibhav.
supposed to.
Vaibhav?
Sorry for that. Yeah. Yes, ma'am. Tell me. Hello.
Hello, Vaibhav.
Yeah. Can you hear me? You have any questions?
Vaibhav, you
Will
are
we
done
get-
for the session or there some more to
Yes.
go?
Yes, ma'am. No. We am done with the session. People are asking, are we
I think,
getting lunch break or not?
We got delayed
Sorry.
in the first session itself, right? There was because of meditation.
Yes.
They
Yes.
have, we could,
Correct. I tried to
give
cover.
them
I tried to
event.
hurry it up, but I was not able to keep up the time. Sorry for that. I lost track of time actually.
Yeah, next session you can continue. Okay, the
Yes,
same
yes.
thing,
Thank you.
whatever you wanted. Sorry, I interrupted you.
No,
Let us.
I was about to
Because,
finish.
they have to come back to the next session. That is by 2 o'clock. So
Yes.
let us break
So-
for the lunch. Sorry,
Yes, thank
Vaibhav, I
No. I'm
interrupted.
actually done with the session. Yes. Thank you.
Yeah, thank you so much for your colorful sessions with so many colors, using all those, making the session very interesting to the participants. I
Thank
hope
you.
they must have enjoyed. So, okay, thank you, Vaibhav.
Yeah,
We'll
thank you.
break for lunch. I hope the next session starts at 2 o'clock by Brijesh, the continuity of electronics and other parts. Okay,
Yes.
okay, thank you all.
Thank you.
Thank you, Vaibhav sir.
Thank you, sir.
Thank you,
Thank you so much.
everyone.
It was a great session indeed.